Sir, actually, I tried for Python but couldn't. Like I couldn't do it initially, so then I switched to MATLAB only.
The issue means
So
see.
not an issue. Like it was taking more time in Python, so I did it
Hmm.
in MATLAB itself.
So none of you tried in Python.
So Shaurya and I wrote it in Python also. It is almost the
Yeah, that's what
same.
I want. That's what I
Yes,
want.
yes, sir. Written in.
Yeah, I also did in Python, sir.
That's what I want. That everyone should not go in one way only. Okay, some variation should be there. Please, I think you should be able to share the screen.
So should I start?
Yeah, yeah. Please go.
Shaurya, you'll show Python, right? Or MATLAB?
We'll start with MATLAB first.
Okay, okay. All right. Sir,
Hmm.
yeah. So, sir, this is the first
Show me the
like
problem first. Problem
problem.
definition.
Then
Okay,
I
because
like problem, sir. I am
that
not
slide will be there, no?
slides. Okay, yeah. Like I will have to open drive link, but okay. This is the first problem. Hello.
Yeah,
Yes,
yeah,
Hello.
you're audible. Go
yes.
ahead.
So here volume fraction was given, correct?
Here, yeah.
No, we need to calculate volume
Okay,
fraction.
we have to calculate volume fraction of fiber and
Weight
matrix.
fraction is given.
Yeah, with the density on y-axis, sir.
Okay, so what is given? Fiber density. Density is the given.
Yes.
Okay.
So
Okay. Hmm.
yeah. So first, what I did was like just assign the density of fiber,
Hmm.
then of matrix.
Hmm.
After that, taken 50. I should have taken 51 points. So
Hmm.
I had taken like 50 points
Hmm.
for fiber,
Hmm. Hmm.
weight fraction of fiber, and then 1 minus weight fraction of fiber will be the weight fraction of matrix.
Matrix.
Yeah, then directly applied the formula for
Hmm.
rows,
Hmm. Hmm.
that we have 1 by like this formula in whole to the power minus 1,
Hmm.
like that was formula 1 by rho c. The formula was given in 1 by rho c
Hmm.
in
Hmm.
slide.
Hmm.
After that, plotted against weight fraction in x-axis and rho c by 1000, as like you have plotted in like you have plotted like 1.2, 1.4, 1.6, and the
Hmm. Hmm.
density was 1200 and 2500. So
Yes.
for
Yes.
that, divided by 1000 here,
Hmm. Hmm. Hmm.
and we plotted in red color.
Hmm.
So that was this. Then after that, label the x-axis and label the y-axis.
Hmm.
Yeah. This was for this one was for first,
That was
this
for the
graph,
first
density
problem.
versus weight fraction. Yeah,
Yeah.
first problem, first graph. So
Hmm.
for this is the, and this will be just a second, figure one. Figure one. Just a second, sir. So, sir, this is
Hmm.
the graph,
Hmm.
composite density versus fiber weight fraction.
Hmm.
And after that, for second one, it was just we have to do. Second graph was of volume fraction versus weight fraction.
Okay.
So directly for that, yeah, also the formula was directly given that
Yeah, yeah.
the Wm, like a weight fraction of matrix into density of composite whole
Hmm.
divided by density of matrix, and
Hmm.
same almost similar formula was for volume fraction of fiber.
Hmm.
And this is the total that volume fraction, Vm plus Vf, that is
Hmm.
Vc.
Hmm.
After that, we have divided all the points taken by Vc. Like that was Vc, the volume fraction of composite,
Hmm.
uh,
Hmm.
and
I
volume
think I think
fraction.
capital VF is the volume fraction. VCVF
But
VM are
sorry,
the volumes.
what I am missing here,
Yeah, yeah.
you have made the it in a very basic manner. But I told that if you can include one function,
It's a import one function.
no, not include one function, like you write a function separately somewhere and you
Okay.
call every time. So in that case, the length of your code will be short. You need not to write everything here in the main program.
So the thing is that we are only using each of these equations once. So
Hmm.
Yes, sir.
even if we
We
create a
don't
function, it
require.
will not really serve its purpose, sir,
Yeah, yeah,
unless we are
correct.
using the
But
same
what
for.
is the thing now? What is the thing? I know that this can be done in this way very we can do it easily. But what is happening as we go ahead in the course and the complexity increases when we have lot of different calculations. That time,
Okay,
if you bring
okay,
the
sir.
function, then few of us will be uncomfortable in that situation.
Okay, sir, no
So
issue.
from
This
the from the
the
from
same code can
yeah.
easily be converted to the
Uh,
function.
because what happens here side by side you can show that okay, this is the function which I'm going to call every time whenever it is required. So in that case, the number of lines in your main program will be less because if you have lot of commands in your main program, sometimes people they lost the thing what is going on in between. Okay,
Okay, okay, sir.
uh, that's what I wrote, especially that you use functions there because anyway I can see loops are there.
Sir, but yeah,
Mm.
sir, loops are not there.
And a loop should be there. I think you should be
Sir,
using
no,
that.
the thing is that when we use this linspace and then when we
Yeah,
use dot and star, it is shorthand notation for the loop
yes, sir.
in
This
both
is the
MATLAB and Python, sir.
Okay.
So
in
it will run over the loop on its own. It is understood that it is going over each of the elements in that array.
yes, sir.
Hmm.
So here, like linspace, sir, for 50 points, we have taken linspace,
Hmm.
and it is a type of loop only. Like it is covering 50 points
Hmm.
at equal
Yeah,
distance.
that is an array, a one-dimensional array.
Yeah, sir. What I mean
Yes,
to
sir.
say is
One
that,
dimensional array, like
Hmm.
storing values in one dimensional array.
Hmm.
sir, if you see,
Hmm.
for example, for row C, sir, you have
Hmm.
WF dot slash
Hmm.
row F. So that
Okay, I
means
didn't know
that for
this
every
thing.
element in
Okay.
WF, it is
Okay.
being divided by row F.
Okay.
So, sir, like
So in
I
that
think
case, we need not to write a for loop here.
no, no, no,
No
sir.
need, sir.
Like
Even
all
for
the values will be covered in this.
even for Python, sir, if
Hmm.
you're using NumPy and yeah, if you're using NumPy, you can do
This
this
is
without writing any for loop.
Hmm.
like this is we have
So so then what is the substitute for while loop in that case?
Sir, both of them are taken care of because this dot and the slash is that is not even needed in the NumPy. It
Hmm.
is the the language itself understands, like Python language understands that you are iterating over each of the elements in that array.
Okay, okay. No, no, this means you told that we need not to write any for loop here and we can do
Yes,
like
sir.
this.
Sir,
Correct.
yes,
So,
for while loop also, any sort of
okay.
loop that you need to use to go through elements in an array when you're doing maybe matrix multiplication or
Hmm.
you're multiplying an array with a number or dividing by a number.
Hmm.
Uh, if you use NumPy in Python or if you use that dot operator in MATLAB, it
Hmm.
will do that automatically.
Okay, okay. So this is fine in that case, no problem for me. But the thing is that okay, it's okay. We can go ahead with this, no
So like
problem.
we will convert it into a function and show it to you again,
Hmm.
maybe in the next class.
Sir,
Yes, because once we go to the macro mechanics of composite, they here tell me. Hello.
sir, I just wanted
Yes,
to.
sir.
Yeah, who was there? Someone wanted to tell something.
Yes, sir. I just wanted to
Ian, you're not audible.
know about this. Like when you're asking. Yes, sir. I am here.
Yeah, tell Anne.
Am
Yeah,
I
go.
audible?
I think we are not able to connect well with I am. So
Sir,
you can
I
go
guess
ahead.
my net
Yeah,
is not
so
working
Who was
properly. So
presenting? Hmm. Hmm.
yeah, so directly here we have taken the volume and total volume.
Hmm.
We have taken the volume of matrix. This is the volume. I'm
Hmm.
sorry for last time. This
Hmm.
was the volume for matrix.
Hmm.
I guess I forgot this. And we have like directly divided by volume of matrix by total volume,
Hmm.
and after that directly plotted on here, like plotted. Just a second, it is figure one, figure two. Some mistake is done, sir. I think two. Just a second. Sir, I think I saved the wrong graph. So, yeah, yeah,
No. Figure one and figure two are for the first assignment.
yeah. But
Figure three and figure four are for.
figure one and figure two are same. By mistake, I think I. Mm, actually, sir,
Run this
the
code
this
again.
yeah.
Just run the code again. It will save it as.
Yes, sir. This will be the figure two. So volume fraction
Hmm.
by fiber
Hmm.
bed fraction.
Hmm.
And for second problem, um, problem figure three.
Sir,
So
in the slides, the
Hmm.
third problem that you've given is the same as what is there in the second
yes,
problem.
sir.
Is it so?
Numbers are also the same.
Actually, sir, see what happened in second problem. Like
Hmm.
this is the Python code.
Hmm.
This is the graph for
Hmm.
second problem,
Hmm.
which I am getting, and this is the plot for third problem. Like this is in Python actually.
Hmm.
I
Okay. Okay.
converted that code in MATLAB code in Python.
Hmm.
So that is same as like only two problems are there.
Okay. It's okay. No problem.
Yes.
So what I am telling. So yeah, which editor you are using for Python?
Sir, Python for that I am using notebook, sir. Like what I had used notebook, so
Okay. Yeah, you
Jupyter
can see
notebook.
the images directly there itself.
Yeah.
Hmm.
This file like this I had saved as html.html
Hmm.
because directly that images and all will come.
Hmm.
So
Hmm.
you can present your code as well as the images.
Hmm. Hmm.
In
Hmm.
and in Python we just have to use the libraries like
Hmm.
NumPy and Matplot library for plotting the
Hmm.
graph.
Hmm. Hmm. Okay. Here again, you need not to write any for loop. Correct. Just
Yeah,
simply
No need,
carry
sir.
on.
lens space
The
is
NumPy
taken.
library takes care of it.
Yeah,
Hmm.
NumPy library takes care of that. And
Okay.
here, sir, I had taken 51 points so that if 0 and 1 are included, both are included,
Hmm.
then the difference between 2 points will be 0.02.
Hmm.
So that's why 51 points are taken.
Okay.
This is the code.
Okay. So this was the first problem.
This is the second problem, sir.
This is the second problem. So all.
This is the second problem which I had not explained to you. And
Hmm.
the problem which I explained, like this was the first problem in Python. In
Hmm.
Python, like I had done like this,
Hmm.
and this is the MATLAB code.
Hmm. Hmm.
And sir,
So MATLAB also got an interactive one, no?
yes, sir.
Yes, sir. MATLAB live script.
Hmm.
Figure three, figure four. Yeah. So in MATLAB it looked like this, and in
Hmm.
Python it was like this.
Hmm. Yeah, things will be same only, but only the thing we need to see that how two approaches are there. Both the things are same only. There's not much difference.
Sir, but you are telling to use the function.
Hmm.
But here I doubt because the code is like for first graph,
Hmm.
the code is only of 4 lines.
Yeah, no, that is correct. What
No,
is
no. I think, Shaurya, what sir is saying is that later in the course, when we have to do more complicated calculations, it helps to have a function to do this so that you can shorten the length of the code that time.
Okay.
for that I am telling. I know. See, if I give you a plus b is equal to c, you need not to write a function. Correct.
Okay.
Yes, sir. Actually, I was just wanting to ask about that only,
Hmm.
like necessity of code in this part. But then yes, later on it might be required.
Yeah, because what happens when you go to the macro mechanics of composite, there we'll have stiffness matrix, compliance matrix, then inverse of the matrix. So a lot of things you have to do in the main program itself. So what we will do, we'll write separate program for each one. You're getting my point.
Yes, sir, I am getting your point.
Hmm.
You are telling to directly make a function for type of formula we have to make it. Like
Hmm.
if we are solving a problem, then
Hmm.
directly we will use function this, that,
Yeah.
and we'll get the answer.
Yeah. So if we want to make any change or anything, we'll directly go into function and we
Yes.
will make changes there. We need not to touch our main program more.
Yes. Got it.
Only for inputs we will use our main program.
Yes. Okay. Yes, sir.
Input and output.
Hmm. So,
Sir, so for the midsem part, we'll have our portion till micromechanics.
Yeah, micromechanics. In fact, I want to engage you guys for some time today. Okay. Once you are done with this.
so should I explain like this second code?
This one, I don't think so. There is no much complexity here
Yeah,
in
it
the
was
Python.
directly, sir,
Uh,
linear. It was that linear function, and
yeah.
directly
So
we are
you
plotting.
need to how you're going to share with us for this.
Directly, I will. If you want directly, I can share this HTML file. I think it will run.
So what you could do is, if you
Hmm.
create a Google Classroom workspace, we can
Yeah.
upload code directly on that, I think.
Hmm. Okay. So okay, it's in HTML format you want to share.
No,
So
I can
we
share
can
in
share a
notebook.
dot py also.
Yes, yes, sir.
Hmm. Where I can use this Python 3 now, what is there? Not means any format should be fine. We can do.
You can directly. I think you can directly copy paste the code.
Yeah, yes,
Hmm.
sir. It will work in Python 3.2.1,
Hmm. Okay.
the latest version which you're saying, right?
Hmm. Okay. Okay, fine. So I think this anyway. It is good that we have started. Okay, we started looking into the problem in a detailed manner, and we will see what we can do later. Hello, am I audible to you?
Yes, sir.
Okay.
Yes, sir.
So let me start the thing. What is where we are, what we were doing before, and I have shared up to,
Sir,
yeah,
and sir, Mr. Amit had helped us a lot, sir. Like,
Amit.
yes, sir. He was like, he was good in Python and he was also good in MATLAB. So
Uh,
he helped me a lot in writing the code.
yeah, Amit is from Bangalore, correct?
Yes, sir.
Okay. So, yeah, in your area, means people are very much they know these things very well. You have these things in your schools also,
Yeah,
I
sir.
think.
That's how I learned, sir. Like
Yeah,
Python is something I learned in school.
yeah. So it is good. Just wait, I want to share the things with you guys. I was there. In the last session, we spoke up to major Poisson's ratio. Okay. I am sharing. Maybe I need to write also. Are you able to see the slides? Hello?
Yes, sir.
Yes, sir.
Okay. So, last we till now we have seen that this mechanical properties or of composite, mostly the stiffness, okay, stiffness values. We had three approaches, okay, that was maybe if I just go and put it together. These are the mechanical properties. We have just taken a lamina, okay, that is on the two-dimensional plate, okay, and the loads are applied, and we want to calculate what is the Young's modulus in longitudinal direction. When longitudinal, I'm telling about the fibers are oriented like this, okay, and your load is applied in your stress is applied in this manner. In the transverse direction, the fiber is like this one, okay, and your load is applied in this 90 degree to the orientation fiber. So E1 and E2 are longitudinal and transverse shear modulus, and this is called as Poisson's ratio, major Poisson's ratio, and in plane shear model is G12. So these are the three different approaches to get these values: mechanics of material, semi-empirical, and elastic approach based on elasticity. What we found, this one was the one of the most basic one, okay, which you people have used in your code, okay, but we found that there are issues. At least for E1 calculation it is okay, we can go ahead with this one, but the moment I need to calculate E2 and G12, I'm going to we were getting a lot of gap, okay, in between the experimental data and the prediction. So the next approach is semi-empirical, which requires the experimental data also. Okay. See, this was the thing that, see, the experiment, uh, mostly the issue was there in the transverse Young's modulus and in plane shear modulus. You see, the experimental data is how, and mechanics of material approach is like this one. So there is a gap here in the both the cases. So then semi-empirical relationship, we looked at semi-empirical relationship and we found that the Halfen side, their work is more accepted in this one, uh, to find the Young's modulus in longitudinal direction, uh, when it comes to say, in the semi-empirical domain, okay. And but what happens, so this is the way they have told you how to calculate this one, and the derivation is not available with me. So this is how you have to use these things, different values are there, okay, and these are all the things we have explained to you. And then what actually I was doing in that class, elasticity approach. Okay, this is the most basic and fundamental approach. Okay, and which takes care of the equilibrium of forces, compatibility of your strains, Hooke's law in 3 dimension, everything. So this is one of the most fundamental, and it is highly reliable approach. Okay, but the thing that when I started, I told you that how the thing is that we assume that fibers are present as cylindrical in are cylindrical in shape. Okay, embedded in a matrix material like this one. Okay, so the representative volume element, till now we have seen that the representative volume element means one element which if you repeat that one you are going to get the entire composite material. So it was like this one. There was a circular fiber or cylindrical fiber in 3 dimension uh, embedded in the rectangular or a square uh, matrix like this one. However, now the elasticity approach tells us that we have to use a condition like this where your fiber as well as matrix both are cylindrical in shape. Okay, it is like this one. Okay, but the thing that when I went through the literature and now I to get the correct formulation which we can explain in the class, I told you that the things are very cumbersome. Okay, and it is not very easy to explain the derivation here, because I think almost this is out of the scope of your course also, because elasticity approach rarely people are telling in the btech level. Okay, but as we started, so just to get the to know the difficulty in analyzing the composite material as due to the involved anisotropy here. So I wrote you just the direct formula for this one, that in the longitudinal direction where the fiber is oriented like this one in the composite material, and your force is also in this direction. Okay, if the force is in this direction, the Young's modulus what you are going to get will be given by this formulation. So this part you are getting from mechanics of material approach. These terms are self-explanatory. Okay, this is volume fraction of fiber. Em is the Young's modulus of your matrix, and Ef is the Young's modulus of fiber. Then there is a term, big term here, which you need to subtract from here, this entire term. And in this you have other physical quantities also. You have volume fraction and the stiffness of or Young's modulus of fiber and matrix. Along with that you have volume alone, volume of matrix, then you have volume of fiber. Okay, so this is going to be a very cumbersome and it is going to be very lengthy thing, so we will not include this one in your MATLAB or uh, Python assignment. Okay, in this because what is the thing is we are not going to train you guys in writing the formula in MATLAB. Okay, that how big formulas you can write. So we will not include this one in our assignment part. Then similarly, mechanics of approach materials. No, this what is called as through the elasticity approach. If I want to calculate the measure Poisson's ratio, okay, you see this much you are getting from the mechanics of material approach, and then you need to add this big term. Then you are going to get some improvement. So what is the improvement? I will show you. And when it came for the transverse Young's modulus, to get an expression for transverse Young's modulus through elasticity approach, I was really shocked to see that that much work people have done, and this much of things we need to bring. You see here, first you need to calculate this thing. For this you need to calculate G23, because it's transverse direction. So the third way deformation in the third direction also we have to consider. Okay, a lot of things are there, and to calculate this one you need to calculate these things, and M, then M is in the relationship with K star like this one, K star is like this one, and then again these terms are different terms are there, you see here. That that much of research work people have done, and to calculate the G2 value. Okay, you see here. In fact, in the book also it was written that this is out of the scope of first level degree courses. However, for the sake of competition, how to calculate the G23, they are writing an a differential equation here. Not differential, it's a quadratic equation only. And when, so I need to get the value of G23. For that, I need to get the value of A, B, and C. And C, you see here, how much A. A is like this one. Then your B is like this one. You can see even in the book it is given like this one. C, it is like this one. And then in the calculation of C, and you need to get the value of eta M, eta F, okay, and those are like this one. So it is a very lot of things are there to be done, but that is not we are going. Just I wanted to show you because I also don't want to run through all the derivation when we are not going to either use in exams or like this one. But the thing what I want to show you here is this one, this slide. You see here, we started with mechanics of material. Are you able to see or hear the thing correctly?
Yes, sir, it's visible.
Okay, you see here, we started with mechanics of material approach. These are experimental data, which we got from experiment for different fiber volume fraction, the transverse Young's modulus, what I got from the reading experimental test. Okay, you see here. Now, mechanics of approach model is this one. Nowhere near the experimental data. Okay, then you see help and side. Help and side prediction is this one. At least it is spanning some of the experimental data. It is engaging some of the experimental data in this zone. But your elasticity approach, you see, this is, I told you, this is one of the most fundamental approach. Okay, and chances of getting error is very less here. Okay, but you see that much work is required to be done, and you see the prediction is really very good. Very good prediction you are going to get from elasticity approach. So that means, just as a conclusion, if we want to calculate the uh, E1 value for a composite material, I can go with mechanics of material also. I can go with semi-empirical also. No problem for me. But the moment I need to calculate E2 and your G12, the best one is I have to adopt my elasticity model based on elasticity. This is one of the conclusion we can draw from here. So what I am showing you here is about E2. Okay, now you see here, this is the prediction what the from the mechanics of material model. I didn't show you, I'm not showing you the entire derivation here. Again, I'm showing you only the final formula for my G12 from elasticity approach. But at least this formula is not that much horrible what I showed you before here. You see here, if you want to solve these things and do the calculation, a lot of time you require. But at least it is okay. G12, I'm getting with my family terms with which we are very much familiar, like this is my shear modulus for matrix, shear modulus for fiber, fiber volume fraction, like this one. I'm going to get this one. So it is okay, at least as compared to the E2 calculation, this one is. So let's see the comparison of all the things for G12. So you see here, these are experimental data, okay, for different types, for different set of tests. For few batch, they are putting with square blocks, and for triangular few batch. You know, experiments are done in different batches, okay. Like we divide, like first batch is there, second batch is there, and in the first batch we will repeat some 5 experiments, mostly 5. Okay, then we will leave the machine for some time, we'll come next day, again we will take the next batch of the specimen, and again repeat some 5 experiments like this one. So this is the way people are putting here. Okay, but in fact you see here how that is nature. Okay, this is not this is the natural tendency. Okay, or it is governed by nature, that the same material, same type of specimen, same machine, in fact you can say same test engineer also there, but you see that much scatter you can see in the experimental data itself. That much variation is there in the nature. You see here, one data is falling here, one data is falling here. That much difference you can see here. No, this is not, means here you can say for a particular volume fraction, if I consider 0.6 volume fraction, you see here, one data is falling here, another is falling here. You see here also here. none of the data points are coinciding. So this is means what means the reality of nature, that the what God has made. Okay, we have to accept, and this is the acceptance you see here. Now you see that what is the prediction you are going to get out of this one. This I was getting from mechanics of material approach, very away from the experimental data. Okay, and where is the help and shy? And I think I'm not able to show here. Somehow it is not shown here. But you see the elasticity solution from the model prediction from the elasticity for G12 is again very good here. At least it's crossing through the experimental data, and it is spanning some of the experimental data very well. So the model building from the elasticity model is always encouraged. But this is an expensive job. To get the solution for the elasticity model, it's an expensive job. Now we have seen, this composite material. This is the thing which I actually wanted to discuss with you. Composite material, are you able to hear me properly? There is no issue.
Yes, sir.
Okay, so what is there in the composite material? They are known for their lightweight. Okay, composite material lightweight. In spite of that, they have high stiffness and strength. So when stiffness comes, means E1 value, E2 value, then your G12 is there, and strength. So strength is there, means what is the maximum stress it can bear. So different type, it is not an isotropic material like your iron or steel or aluminum alloy, that in all the direction you will have similar strength. Okay, as you change the load direction, like you see here the fibers are oriented like this one. Okay, fibers are oriented in this manner. Okay, again it started showing. Okay, and the load is also applied in the same direction. So this is what situation. This is longitudinal tensile direction, or nature of load is longitudinal tensile load. This one A. Another is longitudinal compressive force. You see here, the forces are compressive in nature. This one, third one is transverse tensile. What is the transverse? Means with respect to the fibers are like this one. The load is applied at 90 degree, but tensile in nature. This is what? This is transverse compressive load. You see, the load is applied at 90 degree with respect to the fiber, but it is compressive in nature. This is another type of loading. And here, this is, I don't have any normal forces here. Instead of that, I have shear force here acting on this one. So when I'm going to analyze my composite material, I'm going to get different strength value of the composite material in all the cases. If it was an isotropic material, I will get only one value of the strength material. Mostly one value in the, at least in the elastic region. Okay. But here you see here we will having a different thing. So what are the strength parameters? How you will going to quantify, or how you are going to characterize your composite material based on strength? Till now we have seen about the stiffness value, that which composite based on the fiber volume fraction, which material is going to have higher stiffness in the transverse direction, then the longitudinal direction, then your in plane shear direction, like that one. So now we will look into the strength. We will classify our composite material. Always we look into the mathematics of the composite material deformation in terms of strength. So these are the 5 things: longitudinal tensile strength when I'm pulling like this one, longitudinal compressive strength means how much maximum stress it can bear when the load is applied in the compressive manner. Then you have transverse tensile strength. So this is the situation. Then you have transverse compressive strength. Then this is the situation. Then you have in plane shear strength. This is the situation. Okay. So we have to see all the critical stresses value in all these 5 different types of modes of failure, we can say, for my composite material. So let's see how much we can do here. So you see here, I told you when the fibers are aligned, like this one, and you are pulling the load. It is like this one. And when the fibers are aligned along the direction of your uh, loading direction, means the load is aligned along that fiber direction. This is the, so this is telling you about the tensile strength, okay, and angle of orientation of fiber or stresses. So you see at the maximum strength what the composite material is going to provide you is in this situation. Maximum strength means 0 degree oriented, means the angle both the fiber and the loading directions are parallel, and minimum strength you are going to get when the situation is like this one. And in between, the moment they start changing the different angles, you are going to get the different variation like this one. So what happens actually when the fiber fails, okay, either you will have different, when the composite material fail, the load, when you apply load here, so what are the different types of failure it can have? There can be transverse cracking, means crack going in this way, and this happens for the matrix material. Or fiber rupture, you see fiber has just broken in between at some place, and this is one of the very important failure in composite material. This is called as fiber pull out. What happens? Fiber will break and it will just come out, it will start coming out, fiber pull out. Then you have your interface breakage is there. So that's what I'm telling you. When you see that the composite material has failed, it is very difficult to say that which thing actually caused the failure of composite material as a whole. And this was not the case when I was having my alloy. If alloys are there and I'm putting alloy like aluminum, steel is there, okay. So if there is a failure, I will find that some crack is originating, somewhere crack has initiated. So everything is metallic here, okay. Along the grain boundaries, the cracks are moving. But here, I'm not very sure that the failure has caused by transverse material matrix failure, uh, fiber pull out, fiber matrix debonding. Lot of things are there. So it is a bit complex phenomena to this matrix, this composite material failure. So we'll start with the first one, longitudinal tensile strength. This is one of the most basic type of uh, strength parameter of my composite material. What is there? We so okay. Now first thing I'll tell you. See, this is an important graph for you. If you take fiber alone, and you pull it, the fiber will fail after some time. It will not show any type of plastic deformation, means linear, then hardening type, then necking, and then coming, and then fading. This is how your atypical metals will response of your typical metals stress resistant response. But for for composite material, where your both fiber and matrix both are brittle, you have glass fiber, carbon fiber, okay, these are brittle material. So in that case, you will have data point up to here, okay, you don't have any UTS. In fact, this and here up to you have yield stress. So UTS will shift here only. You whatever the point you can say is the yield, that is called as the UTS also for your brittle material. So you see the if you pull the fiber alone, the fiber will fail at some point where it will fail at a higher load, okay, as compared to matrix. You see, but matrix will fail at a higher strain. You know why? Because matrix are mostly polymers, plastic material, okay. So definitely it will elongate more, but it will fail at a lower stress value. So these are the two extremes, fiber and matrix alone. The moment you mix both of them and make a composite material, then the property will inherit the it will inherit the both the things. Some average type of thing will be done here. So you see here, this is the failure of your composite material. Less than fiber in terms of stress, less than fiber and more than matrix. It is something like this one. So in the longitudinal direction, how we are going to do this one? In the longitudinal direction, the composite material whatever we make, uh, here the fibers are aligned in this direction, okay, along the loading direction. This is the, you are going to pull it. Okay, so the failure will happen like this one. The failure is like this one. So I need to calculate what is this value, because I know what is ultimate strength of fiber and ultimate strength of matrix. I know these things. So if I know UF, UTS and U M UTS, then what is sigma composite UTS? This I want to know in that longitudinal direction. Okay, just leave this one. This is also not required here. Okay, so to calculate those things, we see these things are known to me. Okay, these things are known to me. Okay, so now you see here the ultimate failure strain of the fiber. How much is the failure strain of the fiber? I can get from, if I know the Young's modulus, I can get, if I know the Young's modulus of this one in the one direction, I can get. So this is the Young's modulus in the of your fiber. This is Young's modulus of the matrix material. So I can get the strain values, these two strain values. So there is some meaning for this one, strain values, why I'm to calculate. Okay. Then what is happening? Fibers carry most of the load in the polymer matrix composite. Most of the load bearing structure or component in your composite material in the transverse direction is your fiber only. Thus, the composite tensile strength is given by this one. Same as your what is called rule of mixture, or you can say mechanics of material approach. You need to have the fiber volume fraction of your fiber and volume fraction of your matrix. 1 minus Vm is Vf is Vm only, and you have to put these values, then you will get the ultimate tensile strength of your composite material in one direction, because you know this is the direction in which you are pulling the fiber along the putting the composite material along the fiber. So this is how the number one is coming here, because ultimately then you will see E1 will come here. Now there are few things here that is very important to understand. Okay, what is there? Okay. Now you just assume that you have uh, matrix material is there and you have fibers in this one. So what will happen if you apply load, and as in the transverse, in the longitudinal direction, fibers are going to bear more load here, take more load, let it fails, the fiber fails. So what will happen if all the fiber fails? Do you think that the composite material will as a whole will fail, or composite material will be still able to bear some load? This was the question actually. Okay, that uh, in the situation when the fibers are broken, so what will be the role of composite material alone there? Okay, so the in case you know this thing, when the fibers are not there, the stress that the material matrix can take will be this much maximum stress.
So
Yeah,
here it is mentioned only if the stress is greater than sigma 1 UTS. Should it not be less than sigma 1 UTS?
which one? If only stress it is possible.
So like in this slide, it is mentioned that
Yeah.
if the stress is greater than the ultimate tensile strength, it's possible for the composite to take more load.
If only if this stress is greater than what I wrote, is it possible? Okay, let me go. I think this slide I need to arrange. Come here, I will show you one thing here. This is the thing actually I wanted to show you in this one. See what is there in this one. This is a plot. This one from here to here. This fiber volume fraction I am putting here on the x-axis, and on the y-axis I am putting about the ultimate tensile strength of my composite material. Okay, so in case, so this expression gives you about the ultimate tensile strength of my composite material, which is a function of your tensile strength of your fiber and tensile strength of your matrix, both the thing. Okay, so the So this will be the my response. The plot will be like this one. Okay. And in case if there is a failure, all the fibers are or have failed. Okay. And in that case, I will have only the composite, the strength of my composite material will be alone dictated by the strength of my matrix. Okay, like this one. So if I plot for different values of volume fiber volume fraction, and if I know this thing, I will get an line like this one. Okay. Now you see here, there are few things here, very important things. Okay. So this point, if you see this point, okay, here what is it is telling you that the strength of your matrix and strength of your composite as a whole will are is same here. Means up to this volume fraction, even if you the strength of your matrix and strength of your composite is same. But what happened before this one? Before this volume fractions, you see here, before this volume fraction, strength of your matrix is larger than the strength of your fiber composite material. Are you able to see?
Yes, sir.
You are getting. So this means the volume fraction of fiber, which is possible, is called the minimum volume fraction. So this much of the fraction of fiber should be there in the material, which ensures me that the strength of my composite is greater than the strength of matrix. Are you getting the point or not?
Yes, yes, sir. So my
This,
question was that in the next slide, it is
yeah.
written that if the load is greater than sigma UTS, then the composite can take the load. But if the load is greater than sigma UTS, like the ultimate tensile strength, then won't the composite break?
No, no, this thing I need to. That's what I'm thinking. That why I'm putting this problem, this slide alone here. Something I need to correct it here. But are you able to see this thing or
Yeah, yeah,
not?
I'm able to understand this graph, sir. Like this is very clear.
Okay. Now one more thing. So there are two things are there. Okay. We need to calculate what is the minimum volume fraction of fiber that should be there in a composite material, which ensures me that the strength of my composite material is greater than the strength of my matrix, and that tells from here this point. And you should see here. So this inequality will hold. Okay, means this is strength of my this one. And so if I put rearrange the things, so this is the minimum value of my this one fiber volume fraction, which ensures me that the strength of my composite material is greater than the matrix. This one, we should remember this one. Okay. Now another thing is there. I made it that it's okay that strength will be now. If you see here at this point is also going to be important for us. What happens at this point? This point tells you that this is the ultimate strength of my fiber composite material. No, this point tell me the ultimate strength of my matrix material. You see here, what is this one here? VF is 0. If I put VF is equal to 0, I am going to get this one, the maximum value of my strength of my matrix material. Okay. So this is again an important thing. Now you see here, one thing I just do. So this I got that what is the minimum value of fiber volume fraction, which ensures me that the fiber volume fraction should be more than this one. Then my strength of my composite will be more than your strength of my matrix. This is okay. So that means that then is there any upper bound of my fiber volume fraction? This is the lower bound. You are getting my point.
Yes, yes, sir.
Okay. So if we keep on increasing the fiber volume fraction, that means if you are adding more and more fiber into the structure, do you think the strength of the composite material will increase? I got a minimum value of my fiber volume fraction, VF minimum I got. What will be the maximum one? Or it can go to till whatever we want. No, this is the, because interesting, by adding more and more fiber to the matrix will decrease the ultimate strength of the composite material lower than the matrix. What is happening? If you are adding more and more fiber into the composite material, what you are actually, what is this one? This is your broomstick. Okay, it is something like that, a plastic broomstick you are having. You are having only fiber and no matrix is there. Do you think it is going to have a very high strength? Because now the self aberration and lot of things will start coming into play here. Okay, so this is what the interesting part in composite material, that in fact the fiber volume fraction also has a upper bound. We can't keep on increasing the fiber volume fraction always. So the fiber volume fraction for which this is possible, okay, is like this one, this thing. This value should be greater than my this one. Which one it is telling that? And the critical value of fiber volume fraction, the maximum one is given by this one. Fiber for which this is possible, the critical value of fiber volume fraction that should be there in the structure is this, given by this one. Maybe I need to correct because both the inequalities look same for me, because it is giving me the minimum value, correct? Okay, and this is also a minimum value. This is also minimum value for this one, that critical value of fiber wall, that the maximum or the upper bound of my fiber. So I will always have a fiber volume fraction maximum value and fiber volume fraction minimum value. Below, between these two only we can mix the fiber into the composite material. Okay, so these things, some problems I may ask you in the exam also, that I may give you the values and maybe I'll do some other tweaking of the parameters, and then you need to find me, you to show me that what is the minimum value of fiber that can be there, so that it can it can make it is meaningful for us. Otherwise, you know, the strength of my composite material as a whole will be less than your matrix material. Now this is the thing I told you, and longitudinal tensile strength means now here we are applying load in the this direction. And so different types of failure modes are there, okay, in the longitudinal direction, and it depends on your fiber volume fraction. So you see here, this is about a typical, I think, boron nitrate case. They have shown that if your fiber volume fraction is between 0 to 0.4, okay, the failure is like this one. Brittle failure, everything is breaking like this one. Now, in case of this, in fiber volume fraction from 0.4 to 0.65, there will be breakage also, and there will be some fiber pull out also. Fibers are, you see here, it is pulling out. Means what is pull out? Or it is very easy to see here. Here there is a breakage, but you see the fiber ends are intact. But here you see this fiber has broken and it is coming. It left this end, and it is coming out here. You are able to see the difference here. This is called as fiber pull out. Okay, and fiber pull out with fiber matrix debonding. This is another type of failure which happens when I get a larger volume fraction. You see here, when the volume of fiber is increasing, the strength, the failure is like this one. Now another thing is that this one, how many of you are still there in the call? Hello,
Sir.
Amit has left, I think.
Yes, sir.
Yeah, he will rejoin, sir.
Okay, yeah, he told that he has some issue here. Now this part, actually, the longitudinal compressive strength, you see here the fibers are like this one, and you are applying a compressive loading. Okay, so what happens actually, Surya and other guys, when I was exploring this thing, I wanted to discuss with you guys. I started with lot of energy that I should tell you, but what happened, it is very, very complex to analyze. Why? Because there is a, you know, buckling is coming into play here in this type of loading. What is happening here, in a unidirectional composite lamina under longitudinal compression, the fiber acts like teeny columns and they tend to buckle. Lot of things, local buckling is there, then out of plane buckling is there, then this lot of things are there here. So what happens when this formulation, in fact the formulation also, and the final derivation is a very, very tedious task. Okay, So just leave it. We will not touch this part here. Okay, we will not discuss anything about the longitudinal compressive direction. You will not have anything in the exams also. No, in the exams also, I will not. So we will have longitudinal tensile strength, up to longitudinal tensile strength we will have from this part. Now, transverse tensile strength. You see here, what is there? Now the fibers are like this one. You have fibers, matrix is there, but instead of the loading in this direction, instead of loading in this direction, I am loading in this direction, 90 degree. This I am telling you repeatedly in every class. Just you have to remember, longitudinal means along the length, you should along the fiber length, and transverse means perpendicular to the fiber, like this one. Though they have shown the fibers like this one, no, but the fibers are like this one. Okay, fibers are like this one. You have to assume fibers like this one. So the what is the strength of the composite material in this type, in this situation? What is the strength? So the transverse is a critical parameter, and this is called as first ply failure. No, this is going to a bit important for us. You know, first ply failure is like this one. You see, if you plot the stress strain plot for a metallic material, how you get? You get a straight line, okay, and then you reach up to yield point, and then some deviation will start. Non-linearity will come. This is my called as yield strength. In composite material, a similar analogy they have made, and they have told that you have linearity, and the moment you have some non-linearity, not very high, okay, some non-linearity, that is called as point of first ply failure. It tells you that at least one of the ply or one of the fiber has failed. It is an assumption. The moment you see some type of deviation from the linearity, we say that at least one of the fiber either has failed, or there is a fiber pull out, or something has happened into the structure. So the response is like this. We are using the word for being in a safer side, because we don't know whether the somewhere matrix has cracked, or somewhere the interface between fiber and matrix has broken or anything. But we assume, okay, at least, and this when I'm seeing situation like this in experiment, I will tell, okay, no, at least one of the fiber has failed in the composite material. This is called a first fiber failure. So this is the transverse tensile strength is actually used in the numerical or model building to find the situation when the first ply failure will happen. So you see here, I'm pulling the structure like this one. Okay. So the deformation in this direction, what is happening to the composite material, will be equal to the deformation in the matrix and deformation in the fiber. A sum of this thing given by this formula. Okay. Now it is a bit okay. We can with this type of the study we can do, because it's not very cumbersome. Okay. So the deformation you see here is like this one. Now, so how, you know, this thing that strain is equal to deformation by length, initial length. Okay. So deformation, how you'll write deformation? If I want to write, I need to get the value of strain and the initial length. So here the thickness will play the role of the initial length. Okay. So that total deformation of my composite material is this one. Okay, and this is the this is this is the average. I am telling average thickness of my composite material. I is putting like S, and this is the thickness of my fiber. Okay, so what is this one? Strain in the composite material into the initial thickness, and strain in the fiber into the thickness of the fiber, and strain in the fiber, and strain in the deformation in the matrix will be equal to S minus D, and this one like this one. So where your E, M, E, F, E, M, and E, C are the transverse strain in the composite material. Okay. So the transverse strength in the composite material, what I need to do, if I put all these values here, this here, and this here, I will get an expression like this one. Okay, where I should know the value of my D value, S value, EF, and EM. Okay, and in case what happens here, I told you there are two situations. One situation is when all two situations are there, iso stress and iso strain situation. When all the fibers are aligned like this one and I am pulling like this one, here our assumption is that the strain in fiber is equal to strain in matrix is equal to strain in composite material. However, when the load the fibers are like this one, okay, and I am applying a transverse load here, it is assumed that the stresses in fiber is equal to stresses in matrix is equal to stress in composite material. This is called as iso stress situation, and this is called as iso strain situation. So this situation is my iso stress situation. So the stresses in fiber, I stresses will be equal to stress, means stresses in fiber will be equal to stresses in matrix, and this I can write in terms of Poisson's ratio. This one Young's modulus and strain. So I can, instead of this one, when I have EF and EM, I can write in terms of this one also. But still I'm carrying one of the strain term, that is my strain in the composite material, strain of my matrix material. But what happens when the loads are applied in this way, in the transverse manner, most of the time failure happens for matrix material, because you see here this image will tell you all the things very you see here, when the load is applied in the 90-degree, you have minimum strength, and here you have maximum strength. So here what happens, along the when the loads are applied like this, I applying a load like this one, matrix will start failing here. Nothing is going to happen to the fiber, because fibers will not fail in this shear direction, this two direction. Matrix will fail because matrix is very bulky here now, and it is going to fail like this one. Crack will initiate from this matrix like this one. So when the matrix is going to fail in this compressive direction, then this value, actually the strain in the matrix, we can substitute with the ultimate strain in the matrix. The ultimate strain in the matrix, which will be there till when the failure is. So transverse failure of a lamina is due to the failure of matrix. Then the ultimate tensile failure which will be given by this one, and if I multiply it with my E2 value, I can get the value of my ultimate tensile strength in the shear direction. So this is how this is given. So this was okay. We can work on this one. Few problems on exams also, because here it is, at least it was a handy equations are there. But don't look into anything where you have longitudinal compressive strength. In terms of longitudinal compressive strength, the things are not that much. And most of the thing, when I look into the different literatures, I found that many different expressions are there. Okay, few authors are proposing something, means it is a topic of your research. Okay, where people are still working and they're trying to build a very robust formulation for longitudinal strength in the compressive direction. But for at least transverse tensile strength, formula is okay. We can work on this one. So this much is done. So if I just go to the first slide in this, what I was telling you. So no, not this is not the first slide. Yeah. Wait. Yeah. So this is okay. We can have a problem from here, maybe one problem here. We will not have any problem from here. Okay. Then we can have one problem here also in exams. Okay. And up to here, I told you, and these two things are remaining. Only these two things are there. I need to tell you. Then we will close the our this content of this paper for till midsem. Okay, these two things I need to tell you. Maybe again we'll meet tomorrow for some time. Half an hour I will take, and then we will not meet after that. If you want, you can meet for any clarification or anything. Then we will not meet. So is that fine for you?
Sir,
I'm
yeah, I would like to say, sir, like I have two exams on 9th. So
nine.
since we have the paper on 15th, can we meet on Saturday, 12th March?
12th month, I don't have any issue because, but let me just check my duties also, okay? Because we are also assigned few duties, examination duties are there. So just upfront, I will tell you.
Uh,
Oh,
Yes, sir. We will generally meet in the evening, right?
yeah,
So
yeah.
that time
No,
I
no, no.
do.
I have exam in the evening also. So let me check
Okay,
that one
okay. Sure, sir. Sure. Please check.
because we are given a duty from management here, there, physics courses. So you are telling about why it is happening like this. You are
Sir,
telling about.
12th Saturday.
Yeah, I don't have any exam on 12th. Luckily, I don't have any exam. I have an exam on 11th, 14th, and 15th. 15th is our exam only. So 9th,
Yes.
I have exam. 9th, 4 to 5. 11th, 9 to 10 morning. And this is 2:30. So 12th, we will meet. No problem.
All right, sir. We'll meet on 12th then to
Okay.
like finally finish up the part.
Yeah, yeah. We will meet on 12th. Okay. Any
Thank
other issue?
thank
Is
you.
everything is fine?
Sir, please share some examples, sir. Like,
Okay, I
yeah.
will share. I'll share some example. Okay.
Yes, sir. We can discuss regarding the paper pattern and all on 12th then,
Hmm.
if
Yeah,
that's
yeah. Yeah, yeah, we can meet. We'll meet on 12th then. I will also get some time to put on the things and correct the slides. These slides I'll share with you immediately
yes,
after
sir,
this.
and the recording as well.
Yeah, yeah, recording. I think till the last class recording is there with you.